Now, in this lecture, we want to discuss inhomogeneous differential equations, or non-homogeneous, as your book calls them. I've always called them inhomogeneous, so you'll hear me jump back and forth in notation. And the specific method that we want to look at today is the method of constant coefficients. So first of all, for an inhomogeneous differential equation, the solution consists of a general solution, which represents the solution to the homogeneous part, and a particular solution, which is the solution that fits the inhomogeneous part of this equation. So I want to point out here that in the past we have referred to general solutions and particular solutions in the context of initial value problems, where a general solution has some unknown constants of integration, and then the initial value gives us a particular solution, which in the past has been defined as knowing what those constants are based on initial conditions. Okay, in the inhomogeneous equations, general and particular have a slightly different meaning, where general solution is going to refer to the solution to the inhomogeneous equation, or to the homogeneous part of the equation, and the particular solution is found to fit the inhomogeneous part of the equation. So just a heads up that should you see someone asking for general and particular solutions, say on a quiz, and the equation is inhomogeneous, the particular solution is just the solution that fits the inhomogeneous part. So one approach is to use what's known as the method of undetermined coefficients, and this method is used in equations that have constant coefficients. So what do I mean by that? If you look here, the coefficients of y prime and y in this equation are constants, a and b. And so in this case, we can use the method of undetermined coefficients. If these were functions, then you have to use a different approach, specifically the series method or some other method. So this is limited to where we have constant coefficients of the first and lowest order derivatives. Also, notice that Rx, there are some limits on the kind of function that Rx can be. Rx can be an exponential function, it can be a power of x, it can be a sine or cosine, or it can be sums or products of any of the above. So those are the limits, those are the limits of what A, B, and R can be. So the approach here is going to be, first of all, to find the solution for the homogeneous part of the equation by setting R sub x equal to 0. And then we find a particular solution that comes from whatever the given form of Rx is. Now this is a very useful table, because what this does is, term by term, this relates if Rx is of a given form, and those forms are listed on the left-hand side of the table here, then our choice for a particular solution is going to be of a given form on the right-hand side of the table. So, for example, if we have an exponential form, e to the gamma x, with some constant that in this case would be known, then our choice for the particular solution would also be e to the gamma x with an unknown constant. If we have a power, kx to the n, then our solution would be a sum of an unknown constant, x to the n, and then all of the lower powers of x also with unknown constants. And then sinusoidal, obviously our solution will be some sum of a cosine and a sine. Exponentially damped or growing sinusoid, once again, is an exponential and then a sine and cosine. So basically, the undetermined the coefficients are what we're going to be looking at. We're going to be forcing the coefficients to give us a solution that works in our differential equation, particularly when we have an initial value problem. Okay, so here are some rules for the method of undetermined coefficients. So rule number 1, if your function r, your inhomogeneous part, is one of the functions in the first column in that table that we just looked at, then you want to choose your particular solution in the same line of the table, and you determine its undetermined coefficients by substituting that particular solution and its derivatives into your differential equation. The second rule is called a modification rule. Okay. The modification rule says if you have a term in your particular solution that happens to be also a solution to the homogeneous differential equation, then what you're going to have to do is you're going to have to multiply this term by x, or by x squared if the solution is a double root of the characteristic equation of the homogeneous differential equation. So you have to look, once you've determined your form of r sub x, you now have to look at what your solutions were to the homogeneous differential equation and then make a choice whether or not you need to modify your particular solution based on what your homogeneous solution was. Finally, there is the sum rule, which we alluded to before, that if r of x is a sum of the functions in the first column of table 2.1, then you want to choose your particular solution to be a sum of the functions in the corresponding second column. So those are the rules for determining how to do undetermined coefficients. So the basic rule applies when r of x is a single term. The modification rule helps in the indicated case, and to recognize such a case, as we said, we have to solve the homogeneous equation first. The sum rule occurs when we have r that's a sum of terms. Now the nice thing is the method's self-correcting. So if you make a bad choice or you don't put in enough terms, you won't be able to satisfy the differential equation when you plug the solution in. If you have too many terms, you'll get a correct result, but you'll have too many coefficients and they'll come out 0. So for example, in that sum where you had power series sum, some of those coefficients will come out to be 0, usually. Okay, so here's an example of how we might go about using this method and how we might go about using the modification rule. So here's our differential equation, and this is an initial value problem, so we have two boundary conditions that are specified. So the first thing that we do is, step 1, we solve our homogeneous differential equation. So this term on the right-hand side, this exponential term, we're going to set equal to 0, and we're going to substitute e to the gamma x into our differential equation, in its derivatives, and in doing that we'll obtain a characteristic equation. So if you don't remember this, refer back to an earlier lecture where we talk about finding a characteristic equation. And what we can see here is that when we solve this characteristic equation, it's actually a perfect square, and so we're going to get a double root at lambda equals minus 1.5. And then remembering our modification rule for the double root, that means the homogeneous solution is this e to the minus lambda x times a constant c1, and then e to the minus lambda x times a constant c2. So this second term represents the use of the modification rule because we have a double root solution to our homogeneous differential equation. So this is the homogeneous part. Now step 2, we want to solve for the particular solution of the non-homogeneous part. So now let's go back and let's look at this function on the right-hand side and notice that it's e to the minus 1.5x, but 1.5 was our gamma for the homogeneous part. So this falls into that special category where we have to apply the modification rule. We have to apply the modification rule when we previously had a double root. So in this case, for our particular solution, we have to take our e to the minus lambda x, which is e to the minus 1.5x, multiplied by x squared and a constant. So once again, this x squared comes about because we had to use our modification rule because we have the same root for the homogeneous part of the equation as we have for the particular solution of the non-homogeneous part. So now this just shows also what happens when we take the first derivative of the particular solution and the second derivative of the particular solution. Now why would we want that? Well, what we're going to do is we're going to take the original differential equation and we're going to substitute the first and second derivatives into the original differential equation. And so there's some math omitted here. But when you do that, you'll find that every term has this common factor, e to the minus 1.5x, that can come out. And so we then get this algebraic equation in terms of x squared. Now, when you have an equation like this, for every value of c, or every value of x, the value of c has to be such that terms on the left-hand side and terms on the right-hand side are equal. And so this method of equating coefficients is a classic method to solve for unknown coefficients. So what we're going to do is we're going to take terms in x to the 0, which would be constants, and we're going to show that the constant terms on the left-hand side have to equal the constant terms on the right-hand side. And so that'll give us an equation. If we look here, we'll have 2c on the left-hand side, and we'll have 10 on the right-hand side. So that'll give us an equation that 2c has got to equal 10, and I believe I'm missing a negative sign up here. That means that c should be negative 5. Now, if you look at the x terms, you find that the x terms are going to cancel out. I'll have a minus 6c, I'll have a plus 6c. And the x squared terms will also cancel out. So those will give me 0 equals 0. So basically, I end up able to solve for my constant for my particular solution, my coefficient, by forcing it to satisfy terms in the differential equation. So all that really tells me is what is that constant on the differential equation. So now I have that. Now I plug that back in. Remember, our general solution is going to be our solution to the homogeneous part plus our solution to the particular solution. So here's the homogeneous part with its unknown constants, and here's the particular part. So this is what my solution looks like before I apply the boundary conditions or initial conditions. Now my final step is to apply the initial conditions. So first of all, I have an initial condition on x equals 0. And when I do that, I obtain that y at 0 is equal to c1 and c1 is equal to 1. I then take the first derivative of the differential equation, and I'm going to apply my second boundary condition, which says that the first derivative at 0 is equal to 0. So I take the first derivative, and then I'm going to substitute 0 for x everywhere. And when I do that, I get the following equation. Now, since I've already solved for c1, I can substitute that in and get a solution for c2, which is going to be 1.5. So I now have constant for c1, a constant for c2, and a constant coefficient in the particular solution. So I gather together all of those, getting my general solution, which looks like a combination of a power or a polynomial and a negative exponential. So this is an example of how to apply the method of undetermined coefficients by substituting. Let's just quickly review. We basically took our functional form. First of all, we found the solution to the inhomogeneous equation. We then took our functional form, and we noted that we had essentially the same root, the same exponential function, which told us that our general functional form, we'd need to apply the modification rule. When we applied the modification rule, we then took the particular solution, substituted it back into the differential equation in order to determine the coefficient. We then applied the initial value case, or the initial conditions, in order to solve for C1 and C2. If we were not given initial values or initial conditions in this problem, we would not be able to determine the solution for C1 and C2, but we would still be able to determine the coefficient for the particular solution. This is a plot of what the solution looks like, sometimes just useful to plot things. And notice that because we specified our boundary conditions at x equals 0, then we're only plotting for x greater than or equal to 0.